Good afternoon. I want to present you my talk about new features and improvements in Postgres 18. I hope you will find it interesting. I work for a German company called Creative. We offer support for open source products, and Postgres is one of our biggest topics. Here are a few words about me. I am originally from Czechia, now living and working 12 years in Berlin. And I had very colorful professional life, learning very different types of technologies and use cases, usually quite hard way. So let's start. We have again this special time of year when we in Postgres community have first Christmas. Because new version, which is released at the beginning of autumn, always brings new features, improvements, and also triggers avalanche of blog posts, articles, and talks. So let's look into these new features, and I also added links to interesting talks and articles which already exist where you can find details. So the biggest feature definitely is asynchronous I/O. This is new subsystem which allows multiple concurrent file reads. And this implementation in version 88 is only minimalistic. It does not support writes, so insert updates will not benefit from it. And authors explain that implementing this feature was quite challenging because Postgres uses this multi-process model for all backends. So this implementation only covers reads, but even with this, we will see significant improvements of performance for large sequential scans, large analytical queries with group by, copy command, meaning copying data from the table, bitmap heap scans, vacuum, and one article focused specifically on reading operations on cloud databases with network attached storage, which have usually a big latency. As usual, new feature requires new parameters. The most important parameter is this IO method, which says which method we are using for disk I/O. There is this fallback sort of synchronous I/O, which does reading only in one process per backend, but it still uses this new asynchronous I/O API. So old way is definitely gone. We just can switch off by this new feature using this setting. Another options for really asynchronous reads are either using background parallel workers. So setting for this method is called worker, but uses parallel workers. And another option is using IOU ring, which is Linux specific asynchronous IO queue or two queues. Here is explanation on this picture, and you can find detailed description here in this article. This option requires a modern Linux kernel, which might sound strangely because it's not that new kernel. But from experience, I can tell that many companies are still running even older versions. And another condition is that Postgres must be built with support for this feature. And usability is sometimes problematic because there was a comment that some container runtimes disable this Uring option for security. We will see in the near future, but currently using parallel worker processes is a default and recommended option. And to tune this option further, we need to say how many parallel workers we shall use for these operations. So there is this new IO workers setting with default value 3. But articles explain that this number is actually very low, and they recommend to experiment with values between 1/4 of total CPU threads up to 1/2 of available CPU threads. And there are some benchmarks in articles, and I put some of these graphs into these slides. Previous parameters configured which method and how many workers, and now these two other parameters configure the throughput of these operations. This IO combine limit parameter says how many data pages can be read in one IO request. Because Postgres 17 already introduced streaming I/O, meaning it combined multiple data pages into one reading request. And this feature in Postgres 18 uses this implementation, just processes things in parallel. So the setting says default value is 16, meaning combine 16 pages into one reading request, which is 128 kilobytes of data. And this number is quite small. Useful optimum depends on hardware and operational system, because hardware and kernels, they always have some segment sizes, buffer sizes, limits, whatever sizes you can imagine. So there is always some threshold, and increasing value above this threshold as no additional effect. And we also need to understand that this value is actually limited by this hard limit. This first setting is dynamic. We can change it during run of Postgres. But the second setting, this IO max combine limit, requires restart of Postgres cluster. Default is also 16, but documentation says that on Unix-based systems, we can go much higher to 128 data pages per one reading request, meaning 1 megabyte of data. For Windows, they recommend still this 16 because of limitations in Windows. And this is hard limit. If we try to set some ridiculous big numbers here for that IO combine limit, it will not work, because Postgres will go maximum on value set in this static setting. So if we want to tune performance, we must remember that there is this hard maximum limit. And of course, there are two other parameters which already exist in Postgres for quite a long time: IO max concurrency and effective IO concurrency. And we all probably read a lot about tuning these parameters. So just to remind us that this IO max concurrency means maximum number of concurrent IO operations per process, and default -1, meaning that Postgres will select the optimal value based on some other settings. But there is a hard limit for this concurrency capped to 64, meaning maximum 64 concurrent IO operations per process. And this other setting, effective IO concurrency, says how many concurrent IO operations can be executed simultaneously in total. It got new default 16 now with a new version of Postgres, but range is much higher from 1 to 1000. And we probably all have seen articles saying that for SSDs we shall set it probably to 200. But there is also a warning that very high values may actually increase I/O latency for all queries. So this setting can improve performance, but can give us also very bad penalty. And every new feature requires some monitoring. So we have this new view PG underscore AIOS, which will show us for each IO request, its status, result, or whatever statistics we need. And existing view pg.io was enhanced with new columns showing detailed statistics. But as usual, we must understand and remember that some of these features are switchable. There is a parameter always for tracking different types of statistics, and for our features, there is this track IO timing. And it enables additional IO timing statistics. Default is off because this tracking adds some small overhead. Therefore, we must be aware what we are doing. If we switch it on, it will cause some small performance penalty. And on Linux level, we can use classical IO top command. And if we use it, we will see something like this. These are those background IO workers shown on Linux level. How this all works under the hood, how is it implemented? So we can look into code in path src backend storage AIO, and there is a huge README. And this README describes a lot of details, and I highly recommend to look always in code because some descriptions are better than in documentation. Because we are discussing this worker method, there is a file which specifically is dedicated to just this method worker, and it shows nicely how it is implemented. So on startup, Postmaster creates a pool of background worker processes. Each worker is a separate process on operational system level because everything in Postgres runs in separate processes. And these background IO workers, they still perform synchronous IO, and they just read data in parallel. And it is very similar to the mechanism of parallel processing of query. When we have main process, that session, which starts parallel workers for processing query. And since they are all independent processes, they need to communicate somehow. So there is this shared memory segment through which information is passed to the workers and back again. And exactly the same way it is done here. We also have a shared memory submission queue where a request for a new disk I/O is sent into this queue, and this new request wakes up one parallel worker and it starts to read data. There is a comment in code that each woken IO worker can wake up two more workers, meaning one IO request can be processed by three parallel workers. This is also a reason why having just three parallel workers, as is this new default, is not enough in majority of cases. And there is also note in code that in the future they may introduce improvement to make this process configurable. So woken IO worker would be able to wake up n parallel workers based on whatever needs. And this asynchronous I/O, of course, brings some API interface, and this interface is described in this file in the path src include storage file aio.h. And if you want to study it, I highly recommend to do it through this Doxygen Postgres source code page. And there is a file reference for each file, so you can click on this link and you will go directly to file reference for aio.h file, and it will show you nice graph how those functions are being called, descriptions of those memory structures, whatever you need. But it is quite low-level information, so I did not put anything here. If you, for whatever reason, want to use this API, please go to this file. You will find everything here, or at least it is the best starting point for going deeper into other source code. And now let's look at some benchmarks. This graph is from the article written by Tomáš Vondra, who is one of the guys who implemented this new feature. And he published benchmarks showing machine with 24 threads, 32 gigs of RAM, and 4 SSDs combined in RAID 0. And he benchmarked Postgres 17, Postgres 18 with synchronous I/O, Postgres 18 with I/O U-ring, and Postgres 18 with two different settings of I/O workers, 3 workers and 12 workers. And there are several graphs. So why we have more graphs? This first row of graphs is marked as linear 10, meaning data are almost sequential, just with 10% randomness. That second row is marked uniform, meaning the data distribution is entirely random. And there are 3 operations. Each column represents one operation. So first column is index scan, second column is bitmap scan, and third column is sequential scan on the table. And index scan shows no differences because Tomáš Vondra writes that index scan do not use asynchronous I/O yet. They perform only synchronous I/Os still in Postgres 18. But for bitmap scan, we already see some interesting results. And for sequential scans, those results are even nicer. So when we dissect these graphs, we can see that there is almost no difference between Postgres 17 and Postgres 18 doing synchronous I/O. Those operations are slow, and they have almost the same speed for both types of data distributions. So average value is somewhere 1,700, whatever this value is. But if we look at these yellow and orange dots, they represent Postgres 18 with parallel workers. We see amazing improvements. Average is somewhere around 800. So this is like 60% improvement just by different I/O method. And what is even better, that performance is quite similar or maybe the same for both types of data distribution. So either sequential or completely random distribution did not change speed of this feature. So it is very promising. We will see how it will work with real life use cases, but there is a good chance that Postgres 18 can improve performance really significantly. And another article benchmarked specifically this use case for a cloud database with network attached storage. So it is benchmarked on AWS instance with 32 CPUs, 64 gigs RAM, and 100 gigabyte disk with 20,000 IOPS. And smaller value is better. And they benchmarked similar use cases, Postgres 17, Postgres 18 with synchronous I/O workers, 3 different settings, and I/O urine. And that blue line especially is very interesting because this is called cache, meaning nothing is cached in memory. And here we see amazing results. Those workers with higher settings, 6 or 16, they show like 50% improvement. I/O ring shows even better number for cold cache. Interestingly enough, for warm cache, I/O ring seems to have no effect, but workers still have effect even for warm cache. So it looks like that recommendation using parallel workers is really a good recommendation, and it will be a huge step forward for improving performance also here on cloud databases. Here I put some articles about this new feature. I highly recommend especially this talk from Postgres conference in October in Riga. And you can find some additional benchmarks in these articles. So don't hesitate, dive into it. You can learn a lot new details about it. Another feature, very important from my perspective, from my experience, is enabling checksums on data blocks by default. Postgres historically has availability to calculate checksums for data blocks in relations and check integrity of these data blocks if they were not damaged while sitting on the disk. But there is a slight performance overhead for this feature, and on older hardware, that performance was more significant. But in these days, we have completely different hardware, so that performance overhead is around 1 or 2%. But the gain from that feature is really, really significant. And I will explain on other slides why it is a really important feature and why it can be a lifesaver for us. There are some settings which influence this new feature, and I will explain them on other slides. And here I link my article from our creative blog about this feature, and here are also slides from my talk from this year European Postgres conference, where I explained in more details this feature in Postgres 18 and compared it with situation without checksums in previous versions. So what happens when Postgres detects corruption? I forgot to tell, of course, that those checksums are calculated in the moment when Postgres decides to flash dirty data pages to the disk. So in that moment, Postgres calculates checksums, and there is very nice explanation in code that this is done as efficiently as possible. They use special hardware processor instructions for calculating these checksums, so it's very quick. And this checksum, after calculating, is stored in those 2 bytes in the data page header dedicated for checksums. Once Postgres reads data from the disk, data were sitting some time on the disk, they are not in memory cache. Then when they are read from the disk, Postgres recalculates checksum for that data block, which was newly read from the disk, and compares values. And if we have mismatch of those values, standard default behavior is shown here because there is a parameter called ignore checksum failure, which is by default set to off. And it means that query stops on the first checksum error. We will see this warning. Page verification failed, calculated checksum is different, and it will be followed by error, invalid page in block whatever number of relation, which is indicated by these internal values. We can say ignore checksum failure on, meaning skip checksum errors and continue. And in that case, that query will just report those failed pages, but will continue and will process data which are readable. So if we do some aggregation or whatever and see these page verification errors, we must understand that that result which we get is calculated from readable data. Of course, these pages which failed in verification cannot be processed. Well, this is nice to indicate error and what to do with this. So first thing which we must understand is that if a block is damaged, there is no simple way to repair it. We can only restore some backup and replace that missing block or missing data from that backup. But we cannot repair it. This checksum is for finding errors only. It's not possible to use it for any algorithm to repair data. But as I learned in real life, majority of companies can live with some small data losses. What is critical for them is to be able to continue normal daily operations. And exactly for this, we have this second parameter, zero damaged pages. Default is, of course, off. And this parameter does what it says. If it switch it on, it will zero out that damaged page. Meaning, if page verification fails, zero damaged pages is set to on. We will get warning about invalid page in specific block, followed by this zeroing out page message. And that specific data block will be filled only with zeros, like 8 kilobytes of zeros. That way, that block is zeroed out, and it means that that block is now dirty in the memory. It will be flushed to the disk. So we will have now in our data files this specific block filled only with zeros, and later AutoVacuum can remove it. And now when we discuss it, this option, we must understand two things which are which come with this option. First, this is irreversible. If we zero out some page, we cannot go back. Even by setting zero damage pages to off, we cannot restore previous wrong data because they are already gone. It also means that with this setting in the session, we will zero out only those data pages which we scanned in our query. This option, zero damaged pages, is very sensitive, so never ever set on globally unless in some very desperate situation, I don't know. It must be done only proactively on in the session where we know what we are doing. And second thing which comes with this is, and you probably would immediately ask it, what about auto vacuum? If we, for whatever reason, would set zero damage pages on, what will auto vacuum do? Fortunately, answer is very simple and it is done in a very safe way. In autovacuum.c file, which implements this feature, there is this part which forcibly sets zero damage pages to false. And there is a command force zero damage pages off in the auto vacuum process. And they say we don't really want such a dangerous option being applied non-interactively. Because, yeah, we all understand what would happen if zero damage pages would be globally set to on. Auto vacuum will find some damaged pages and it will say, okay, page is damaged. I will zero it out. Well, nice. But we will have sudden mystery about missing data and we would have to investigate it, go to logs and whatever. So this is not allowed. And it's very good that this is not allowed because we must always do what we are doing with this zero damaged pages setting. And these checksums, they have another implication for upgrades. Because new PG upgrade requires both old and new clusters with the same checksum setting. Either must have both checksums enabled or disabled. If there will be mismatch, disabled on old cluster, enabled on new cluster, which will be normal situation, PG upgrade will fail with a checksum mismatch error. There was some discussion during development about adding checksums on the fly during upgrade, but for different reasons, it is not supported yet. So if we are upgrading older cluster to Postgres 18, older cluster does not have checksums, we logically have two options, either disable checksums on the new cluster 2, or enable checksums on the old cluster and then make upgrade. I strongly recommend to go to use checksums. In my talk from European Postgres conference, you will find any good reason, every good reason to do it because repairing corrupted data without checksums is a real pain. It's a really slow and tiresome process. So I highly recommend to use this new change in behavior and go to checksums and it will be beneficial. Even more because binary backups which are done by PG-based backup, they mask data corruption. It is explained in my slides, and therefore we can have already corrupted data. We can have like a long line of backups feeling safe, but the same corruption can be in all of these backups because these corruption are being revealed only when data are being directly read by Postgres. Go for details into my talk and I will continue with these new Postgres features. From my perspective, third big headline, B3 skip scans. This feature already existed quite a long time in other databases, and this is typical situation which users often discuss when we have a B3 index created on multiple columns. We cannot use this index for filtering on a non-leading column Meaning, if we have query in the condition, we must have either first column or first column together with second column or first together with second and third, you know. But if we would have query which will filter only on the second column, not using first column at all, then Postgres in previous versions was unable to use such B3 index and used sequential scan on that table. Uh, Usual recommendation and only remedy for this situation was to create additional index for that second column. Now, with Postgres 18, this skip scan means that it can really skip that first column and read a structure of the index to get values for that second column. But as you can immediately see, this works nicely for cases when that first leading column has very low cardinality. Only a few dozens distinct values. In that case, that reading will be very efficient and performance gain will be significant. Of course, this skip scan will be always slower than using a dedicated index, but it will be in case of low cardinality of that leading column. In that case, it would be always quicker than sequential scan on the table. So some queries can benefit from it significantly. There are two articles which show some examples and benchmarks. I highly recommend to jump on it. Another long-awaited feature is native support for UUID version 7. We all know UUIDs, but internally UUID is generally just 16 bytes integer. It's like 2 times bigger than big int data type in Postgres. We just present it in this hexadecimal string format, so it looks like some rocket science, but internally it's 16-byte integer. And that version 7 suggests that there are already 6 previous versions. And in Wikipedia, you can find description how these previous versions have been generated. What was actually problematic in previous version was that those generated values were randomly distributed over that interval of these values. And therefore, if we needed to use UUID for primary key in our table because either numeric ID was not having sufficient range of values, or we wanted to mask whatever behavior, then that B3 index made for this primary key suffered from very often page splits. And I highly recommend you to look at this talk from PG Lowland conference in Rotterdam this year. That guy from UK did a lot of tests and presents some interesting details about UUIDs. And here you can find also benchmarks for these different types. But version 7 improves locality of these values because it includes timestamp in milliseconds since epoch, meaning this is that Unix timestamp from January the 1st, 1970. And it is in milliseconds, so precision is very high. And those other parts are random number, except for these two half bytes because in UUID definition, these two half bytes are dedicated to indicating version of UUID and subversion. So now with timestamp in UUID version 7, these values will be always properly ordered. So B-tree indexes will be very compact because new value will be just added at the end of last leaf page or at the beginning of a new leaf page. But as it was discussed on European Postgres conference, there is also some small security leakage because if we have this timestamp in UUID and we know how UUID is constructed, we can immediately say when this value was generated, and if we have sequence of those UUIDs, we will see time differences between records. So for some applications, this could be questionable security leakage. Therefore, it's necessary to analyze if we can afford this. But for other applications, this will be completely out of scope, and they can benefit from UUID's version 7 really significantly. There are also some optimizations in Query Planner. And this first one will sound like a big joke to people who are used to construct SQL queries manually, because seeing these so-called self-joins in these selects will immediately raise the question, what the hell this construct should do, why I joined the same table with itself, and so on and so forth. Answer for this question is very simple. These very strange queries are sometimes generated by connection libraries or query builders. And these redundant self-joins made performance suffer in previous versions of Postgres, but not anymore. Postgres 18 can automatically remove them. And there is a small benchmark from these slides from this year European Postgres conference, showing that by removing self-join, and that query was immediately running like 70% quicker or even more. It may sound like some strange improvement, but if there is probably, for example, something like content management system, these web applications can run thousands very small queries against database to read just layout of the page or permissions for user and so on. And some of these queries can be constructed in a very strange way. So just by switching to Postgres 18, these applications can now be performing much better. There is also another article explaining in details. In version 17, we already had improvement for condition where column in subselect. Version 17 was able to rewrite this column in subselect condition as join, and it was a huge improvement in performance because what I have witnessed on older versions of Postgres, this condition always created performance bottleneck. Now in Postgres 18, they are rewriting other cases, and for me, a very important change is this: when we have select with a chain of OR condition on the same column. Again, this type of query is generated usually automatically by code in applications or in Postgres functions in database, and our clients they quite often come with performance issues on queries which use quite a long chain of these OR conditions. So now Planner can automatically optimize it to rewrite it into condition equals operation called any on array of these values. There is another form of this condition, which is slightly more intelligent, but generally also not exactly performant. And we have condition in a list of values. Also, this type of condition is now automatically rewritten in the same operations. And some discussions on internet suggest that improvements in performance are quite magical on some use cases, on some queries. We will see. Another improvements in Query Planner include hash joins. In previous versions, when we joined two tables, order of those tables in query mattered because that first table was always hashed. But now Postgres can decide which of those tables should be hashed, and it will always take the smaller table for hashing. So it can automatically change order of those tables in that query. Also, a huge analytical group by operations will benefit from this improvement. There are some additional improvements which make queries performant. You can find more details in release notes or in articles. I did not find any specific article for these features, but new articles are coming all the time, so maybe you will already find something if you would need to know details about these improvements. Another feature is quite obvious. Those are virtual generated columns, which existed in other databases sometimes for quite a long time. I think this is quite clear. I will not go into details here, and you can find more details in documentation, or you can look later on these slides. But from my experience, this enhancement is very important. Data manipulation commands, insert, update, delete, merge, can have a returning clause. And in older versions, this returning clause was able to return us new values from that query. Now, in version 18, we will get trigger-like behavior. We can access both old and new values. So it is a huge improvement. It will simplify auditing, logging, change tracking, and in some cases, maybe developers will even decide to use this feature directly in code instead of triggers. Instead of auditing triggers on tables, because these auditing triggers can sometimes cause performance issues. So, very important feature with very good implications and possibilities for our applications. Now we will have some security improvements, and first of them is native OAuth 2.0 authentication. I had to look up on internet how to properly pronounce this OAuth abbreviation. This is a shortcut for Open Authorization Protocol, and it's used for token-based authentication on internet without sharing passwords. This OAuth support must be enabled at build time on Postgres. But when it is enabled, it gives us very nice new options for authentication. We can use single sign-on mechanism for database access. We can use centralized identity management providers like Google. We can integrate with enterprise identity systems like Okta. And this new feature is configured via pg_hba.conf file using this method OAuth. I found two nice articles about this new feature, so you will find details there. Although, to be honest, it looks like people are currently only experimenting with these features, but I presume it will be next big thing in coming months when people will share their experiences with this new feature. Talking about security improvements, MD5 hash is deprecated officially, and we cannot use it because this MD5 hash was actually getting quite dangerous over time. Attacker could intercept this MD5 hash and use it instead of password because that MD5 hash was generally used exactly the same way as password, so it was very vulnerable. Now, new default is this Scram salted challenge response authentication mechanism, and this is quite ingenious mechanism of communication between client and server. They send this challenge and response both ways, and that way authentication is being done without sending any passwords, any hash of password. And what is most important here, that this communication is unique in the context of the session. So even if attacker would be able to intercept that communication, replying that communication will not help because those tokens will be invalid when they will be replied in a different context. Uh, Huge improvement I want to mention is parallel creation of gene indexes. Last year I had talk about gene indexes on JSON-B data and TS vector data for full text search. And in my tests, I have repeatedly faced the situation that creation of gene index on large tables took hours, and in case of cloud databases, it was even longer than 24 hours in some cases. Now, fortunately, this is the past, and we now have option to create gene index in parallel using multiple workers. Here is this max parallel maintenance workers setting, which we can change to get better performance. So from my perspective, this is a huge step forward for using these features. Another enhancement are in explain analyze output. I forgot here this word analyze, but I think you understand that showing buffer usage, wall writes, and so on can be done only for explain analyze command. Some improvements in PG upgrade. There is a new swap method, which is intended to swap data directories, to move directories from old cluster to the new cluster instead of copying, cloning, or linking files. And we had some discussion with colleagues how it is actually done, because it looks like that change of speed will not be that huge against other methods, at least against linking. But I looked into source code, and there is huge change in implementation of this feature. Those previous features are really processed file by file sequentially, and now swap method introduces internal queue of requests, and this queue is processed in parallel. We have now this jobs setting for parallel processing. This is another change in PG upgrade beside of those checksums. I presume in the first half of next year, when companies will start to use Postgres 18 in production, we will see more articles about these features and their practical usage. Some improvements in backup. PG dump can now dump also statistics. You can find more in these slides if you are interested. Long-awaited feature is this not valid constraint setting. Meaning, if I want to add some new constraint on a table, I can add it with this not valid setting, and it means that constraint will be created but will be not validated immediately. And now I have more time to play with this value, check it, fill it, whatever. And later in another transaction, of course, when I'm sure that it will not cause any problems, I can simply alter that table and say validate that constraint, and that way we can add constraints like not null or other problematic check constraints without any downtime impact. So very nice long-awaited features. We have new, very interesting feature for temporal constraints. This feature works with a range data types. We have several range data types in Postgres: date range, time step without time zone range, time step with time zone range, and integer or numeric ranges. And when we use these time-based ranges, date and time-based ranges, we can use now this new without overlaps temporal constraint. It behaves like exclude constraint on the range type, and implementation needs also this b3 underscore gist extension, because that new index which is created for these use cases when we use that range column in primary key or unique index. That new index is gist internally. Using this b3 gist extension, we are able to do a range scans on gist data inside that index. There is article which explains it in more details. I created some example showing that we have this very simple subscription table with subscription ID and validity date range. And here is the primary key on both of these values. And that last one is that range column. So we can use on it this condition, this constraint without overlaps. And we see when I insert two records which do not overlap, everything will work. Everything will work here. But if I try to insert data which overlap with both or one or whatever of these values, and then I will get error. And with this new feature, we can use this containment operator, checking if this timestamp is contained in this column. Of course, we can also use it for foreign keys. So here is an example. I have a child table, and that foreign key has also a range column, and I can reference it and use this new keyword period, meaning those child record must fit within parent validity. So it cannot start earlier than earliest validity of that parent, and it cannot end later than latest date or timestamp of validity of those parent records. And last slide is interesting enhancement for handling null values. In Normal SQL standard null is not equal another null because we don't know what is the content, so we cannot say anything about equality. So by default, null is not equal another null. Therefore, if we have multiple nulls, there are all distinct values, which could be problematic for some use cases. So we now have this option to say nulls not distinct. Here in this first example with stable users, if we define this email as text and unique, we can have multiple nulls in those records because they are all distinct from the perspective of SQL standard. But with Postgres 18, we can say that this email column is unique, but nulls are not distinct, meaning only one null will be allowed over all those records. Because this setting for that column immediately creates a unique index with this nulls not distinct setting. And that's everything. Time is up. I thank you very much. If you would have any questions, we can discuss it privately. I hope you found my slides interesting. Here you can use this QR code for finding all my other slides. I thank you very much for your attention and enjoy the break.